Once you open SimulationX, you're greeted by the welcome screen. For this demonstration, we'll go directly to the model. Select File, Open, Browse, and navigate to the location of the virtual proving ground model. Select the model and open it. The required libraries are embedded in the demonstrator so they open automatically with the model. Once the model is open, you can see two main views. On the left is the diagram view, showing the different model elements and how they are interconnected. On the right is the 3D view, which provides the physical representation of the system. The model uses elements from the MBS libraries, giving the components their corresponding 3D representation. The objective of this model is to evaluate the vibration behavior and driver comfort of a wheel loader driving over uneven terrain. The focus is on the vibration transferred through the machine structure, and in particular the loading on the bushings that connect the cabin to the rest of the machine. The wheel loader is modeled using multi-body system components, together with elements from the Power Transmission 1D library. The model includes the major vehicle components, including the cabin, chassis, wheels, and the cylinders responsible for actuating the bucket. For this demonstration, however, the main focus is the vibration transfer path and the bushings. The vibration originates when the wheels interact with the uneven ground. It is transferred from the ground to the wheels, through the bearings and axle, into the frame, and finally through the bushings to the cabin. The bushings, therefore, play an important role in controlling how much vibration reaches the cabin. The other model components are already parameterized. For example, the tire model includes parameters such as friction, radial stiffness, and radial damping. For this demonstrator, we therefore only need to focus on tuning the bushings. To modify a bushing, simply double-click the element. For this demonstration, select the bushing_FL element and open the Parameters tab. Here, we can see the translational stiffness and damping parameters. These are the parameters we will vary to investigate the behavior of the system. By changing the stiffness and damping, we can tune the bushing according to the operating scenario and the desired vehicle response. Once the model has been parameterized, we can define the results we want to observe. First, activate the required protocols so that the corresponding results are recorded during the simulation. For this demonstrator, we're interested in the internal force, displacement, and cabin acceleration. Once activated, simply drag and drop the required result variables into the diagram view to create the plots. Multiple result variables can be added to the same plot for easy comparison. Now the model is parameterized and the required results are ready to be evaluated. Next, define the required start and stop times and start the simulation. SimulationX calculates the response of the wheel loader as it travels over the uneven terrain. Once the simulation is complete, we can analyze the results. Here, we can see the displacement difference, cabin acceleration, and loading on the bushings. These results allow us to evaluate the vibration response and determine whether the current bushing parameters meet the desired design target. If necessary, we can adjust the bushing parameters and run the simulation again to further tune the response. One useful feature in this demonstrator is parameter referencing. The bushing_FL parameters are referenced by the other corresponding spring damper elements. This means we only need to modify the parameters of the bushing_FL element. The stiffness and damping values are automatically propagated to the other bushings, eliminating the need to parameterize each one individually. Although this demonstration focuses on a single bushing parameter, the same approach can be used to investigate other parameters. You can vary parameters of the wheels or other model elements, change the operating scenario, or define a different vehicle trajectory. The resulting influence on the system behavior can then be evaluated through simulation. This makes it possible to quickly investigate different design configurations and understand their impact on vehicle performance and driver comfort.